afternoon, everyone. Thanks to the organizing committee for this session. So I'll start by introducing or acknowledging the co-authors of the NCHRP report that I'm presenting part of it today, Kejan Wang and Peter Taylor and Dr. Shah, as well as the grad students participating in this project. So let me first explain that, as indicated in the report, this was a project on looking at how SCCC can be used in cast-in-place bridge components. So it was not focused on evaluating the supplementary cementitious material, but because most of the state DOTs use mixes with supplementary cementitious materials, we had to try different combination of these materials within that project. That's why it came the idea, how about if we look at the effect of this material on how SCCC will behave. So first I will focus on the types of SCCM that we used in this project. The Class C fly ash, Class F fly ash, as well as slag, and also Class F fly ash plus limestone powder. And we couldn't in that project to go with high replacement percentage, like we all like to have a low cementitious, low carbon footprint, but we had, because it's done by DOTs and they have limits in the specs about what is the maximum replacement you can have. So for Class C and Class F fly ash, we limited the use to 25%. The slag was 30% replacement, and for Class F fly ash and limestone powder, with the total replacement to 35%. So we're talking about the range of from 25 to 35 cement replacement in this project. So what I'm going to present first is the mixtures that we used for SCCC, and then how the different SCCMs affect the fresh properties and early age properties, as well as hardened properties, including mechanical and durability properties. So this is a kind of a simplified diagram that shows the different property groups and the one we studied in this project to evaluate the effect of the SCCM. The one shown in green are the one I'm presenting today. The others, we didn't study a wide range of SCCM. That's why I will not present those, but we'll focus on the green ones. As you can see, mainly workability. For SCCC, that's something very important, and workability retention. For mechanical properties, you can see that the regular mechanical properties are compressive strength with elasticity, flexure, as well as some viscoelastic properties like shrinkage and creep. For durability, you're just going to focus on surface resistivity only in this case. So I'd like first to present what materials were used in this project. We had two groups of mixtures of SCCC. One group that used limestone as coarse aggregate. The other group had gravel. And we tried three different gradations, or three different sizes, pretty much 3/8, ½ inch, and 3/4. And one type of sand was used in all the mixes. For the different powder material we used in the project, of course, cement type 1 cement, and Class F and C, and slag, as well as limestone powder. You can see in the gradation, they're all very close to each other. That's somehow considered not a very fine limestone powder, because of finer types than that, but that's what was available locally for this project. And you can notice also here that the slag pretty much is the finest material used in these mixes. To evaluate the wide range of mixtures from SCCC, as I said, we have to do some with crushed limestone and another group with gravel, and three sizes for each. And within each group, we had to try 4 different types of SCCM that I explained. And we also split the categories of SCCC into a low slump, and high slump. The reason for that, because some bridge application doesn't need to have a 30 inches spread. 22 to 26, which we considered a low slump, is applicable in many bridge components. Other component that has high intensity of reinforcement and very difficult geometry require much higher slump. So we had a group that is 26 to 30 inches. So that shows pretty much the metrics that explain all types of SCCC that we studied in this project, which has a total of 40 mixes. I'd show just, I know it's not easy to read, but just explain some of the properties that we looked at for the mix design. So these are only 20 of them, and we show here the idea of the mix based on the type of size of aggregate as well as the type of supplementary cementitious material and the level of the flow, low and high. Based on that, we designed the mix with different dosage of high range water reducer and VMA as well as air entrainment admixture. So what I'm presenting in the next slides are pretty much trying to see if I group this mixes based on the different SCM, if we're going to get any conclusion about the fresh properties and mechanical properties. So here's two charts, one for the SCCC with low slump. And you can see the boundary here is 22 inches, and the ones with high slump, the 26 inches, and then group those based on the SCCM used. And for every group, you can see 5 mixes, pretty much the limestone and the gravel, as well as the size of the aggregate, 3/8, ½ inch, and 3/4. And pretty much if I look at those, I tried myself to come up with a conclusion. I didn't see really a clear conclusion from that if the supplementary cementitious material type and dosage will affect the flow much. And maybe one of the reasons for that is because we adjusted the high range water reducer and the VMA in every mix in order to get it to be stable and in order to be in the category of the flow that we are looking for. So you don't see a clear conclusion for the effect because you have different dosage of high range water reducer. So that's why I tried to put them in a different way. Maybe I can make conclusion. So I plot the horizontal axis here is a high range water reducer dosage used in these mixes and the flow in the vertical axis, and plot every SCCM in a different dot. You can see some differences. For example, the one with the green triangle, the ones with the slag, tends to have higher flow when have higher demand for high range water reducer to get higher flow, and maybe that can be attributed to having a smaller particle size for the slag. I showed you earlier that it has the lowest size in terms of particle compared to the other material. But again, you don't see a really conclusive result from that. You can pretty much have a wide range of flow based on the high range water reducer. That's more effective parameter than the SCCM itself. So try to look at other properties and how the SCCM can affect that. So this is passing ability using the J-ring and also putting the dotted line around the limits, the limit of 2 inches or less that has a good passing ability. 2 to 4 is pretty much moderate, and more than 4, of course, it has low passing ability. So try to look at the aggregate size in this case, because aggregate size is one of the most important parameters for the passing ability. That's why we put the 3/4 and then half, and then 3/4, half, and 3/8. So looking at SCCM effect and all those, of course you expect the trend to be high and then low because of the aggregate size. But you can see also the mixes with slag here. The green one, which is fly ash and limestone powder, the one that had the best passing ability compared to the others. So it had much better ability to, even with aggregate size, to pass through the ring. So trying to look at the passing ability in a different way, which is a casein test, which is an AASHTO standard. Also, the limits for the casein test is 70% or below is a low passing ability or filling ability. And then from 70 to 85 is moderate, and above 85 is considered very high or good filling capacity. Again, looking at the SCCM and if there is any clear distinction between their effect on the filling capacity here, and really couldn't find, except that the one with maybe class C fly ash, especially when it's limestone, has the lowest compared to the other three SCCMs. But it's, again, it's not very decisive conclusion because you don't see the trend for SCCC with gravel. Looking at the static stability using the column, we did that using the column and using the penetration test as well in the next slide, and with 10% being the limit to consider there is segregation. So you can see from 10 actually to 20 is moderate, and more than 20 is really high. So below 10 is very good stability. And you can see here we have two groups basically. Limestone is one group and gravel is the other. And looking at the aggregate size is actually more prominent effect. The ones with 3/4 inch size are the one that pretty much giving high or low stability or high segregation somehow. But the SCCM itself did not show any pattern or trend in terms of the static stability in this case. Looking at the same performance, which is static stability, but using the penetration test, you can see actually in this, I put the limit here is a 1/2 inch. Below 1/2 inch is very stable. From 1/2 to 1 is moderate, and more than 1 is low stability. And it seems here that what I can see clearly is the limestone, regardless of the size, is much better stability than the ones with gravel, especially if it's gravel, and the 3/4, the one that shows lower stability compared to limestone. But again, trying to figure out if SCCM has an impact or not, or there is a trend, but you cannot see really a big trend in that sense. So looking also at the visual stability index, we know the scale. Scale is 0, 1, and 2. 0 is a very high stability, 1 is moderate, and 2 is low stability. And looking at it again in the hardened visual stability index, which is 0 to 2, and looking at with different SCCM, how many of the mixes had zeros and how many had ones, trying to see if there is any trend there. You can see here the one that has class C fly ash and slag had higher values for 0, which means higher stability, compared to the class F and the limestone powder. But again, there is no huge difference. They're all pretty much very stable, and you don't see big difference in the number based on SCCM content. Looked also at workability retention in many bridge application. Some components require larger quantity. It's important to maintain the workability for a longer period of time. We evaluated that for a period of 90 minutes, an hour and a half, and looked at also mixes at the start between 22 and 26, so low slump, and how that change over time compared to those who start from 26 to 30, and that change over time. And every line shows mixtures with different SCCM. Again, you don't see a clear difference between the different mixes in that sense. One clear observation, if you start with a low flow, you don't lose flow with a higher rate as much as when you start with a high flow, as you can see in the figure at the top. Looking at time of setting, it's important in some bridge applications, especially if you want to open it to traffic or continue construction earlier. So this shows the time of setting for mixes with low slump and with high slump, and you can see the one with green, with the class F fly ash, had shorter time of setting compared to the others. That repeated the same conclusion in both with low slump and high slump mixtures. So this is an effect of the SCCM on different fresh properties. We looked also at some mechanical properties like compressive strength. Every line here shows the mixtures with limestone in black and the ones with gravel in orange, and looking if there is any real difference between different SCCMs. The only observation is very clear. The ones we had with class F and limestone powder showed the lowest compressive strength. That could be part of it because it has the highest cement replacement, 35%, and also might be because of the fineness of the limestone powder. It was not the finest we want to get, but that's what was available at that time. I'm sure that with finer limestone powder and also different dosage, you might get better compressive strength. Just keep in mind that we are not looking in these mixes for the 6+ KSI, because that's for bridge component cast in place, like a pier footing, pier cap, and not bridge girder. This is not for 6,000, 8,000 PSI bridge girders. That's mainly for cast in place application, wing walls, footings, things like that, which is normally, and most of state DOT, they specify from 3.5 to 5,000 PSI. So that's what we were targeting. That's why in mix design itself, you see also low cement content, and that's what resulted in this range from 4 to pretty much 6.5. Looking at the moisture elasticity for all these mixes, again, they're almost the same range. Moisture elasticity originally had a plus or minus 20%. That's by default. And we get slightly less, of course, with the ones with 35% replacement. And that's consistent with the lower compressive strength. Here I put it as splitting tensile strength. The red line shows a prediction, if you use the AASHTO equation, how much you expect to get for a 4,000 PSI concrete. And you can see there is a wide range of fluctuation. Some of them did not make the prediction. That's why, as a result of this work, we proposed a smaller factor, less than 1, to be used to reduce the splitting tensile strength in these mixers. Next one, sorry, I think I skipped one. Okay, this one is a drying shrinkage. I think the one skipped is the flexure, which has the same conclusion of the splitting tensile strength. But here is looking at the plot of the predicted drying shrinkage using the AASHTO LFD formula and the measured one for all the mixes grouped by the SCCM. And you can see clearly from that the ones with class C fly ash is the one that has highest shrinkage compared to the measured one. You can see the coefficient Y equal coefficient times X, the one that's about 58% higher in this case compared to the one with class F fly ash. It gave 1.28. So a big difference based on the SCM. So that was a decisive factor here, the type of supplementary cementitious used in this study. Looking also at dry, restrained shrinkage, which is very important in applications like bridge decks, where you have restraining from girders, and you look at how the chances of having cracking, and you can see this one I compared only with the conventional concrete, because with conventional concrete we had only one SCCM mix, which is the one with fly ash F. And again, you can see the mixtures with Class C fly ash had the highest shrinkage, restrained shrinkage as well as drying shrinkage. Okay, looking at the creep effect, and again, the line with black line is the one with conventional concrete, not SCCC, with Class F fly ash, and all the others were very close, actually better or lower creep strain, except the one with Class F fly ash and limestone powder, which has 35% replacement, give the highest creep strain, and this also required a modification factor to be considered in the prediction equation. Last, the property, we didn't study many of the durability properties, but one that we applied to all the mixtures was surface resistivity, and this is because it's an easy test to do for a large number of mixes. And you can see the first group is the conventional concrete with Class F, and the others are all SCCC, and the one that showed the highest resistivity is the one with slag, regardless of the type of aggregate or the size of aggregate used in all of them. And of course, higher than 12 was considered moderate resistivity. So I will conclude from that few items here. One of them is that regarding the fresh properties, especially the workability and workability retention, we didn't see effect for SCCM that is clear we can make conclusion about. More effect comes from the type of aggregate, the size of aggregate, and the dosage of high-range water reducers. So it shouldn't be something you worry about, what type of SCM and how it affects. Of course, it has some effect, but it's not across all the mixes we tried. More effects can be seen in, for example, the time of setting. With Class F fly ash has delayed, has shorter time of setting, and when you see mechanical properties, the ones with limestone powder showed less compressive strength and higher creep strain, and the one with Class C fly ash showed the highest shrinkage, and the one with slag showed the highest resistivity. So that's based on the 40 mixes we tried, and that's basically summarized what we have done in this project. Thank you.